Today we are going to discuss about extreme metal poor stars in the Milky Way and the nearby satellite galaxies in the context of near field cosmology. So, what are metal poor stars? So, the extreme metal poor stars are defined as stars that have lesser heavy elements compared to the most metal poor globular cluster in the galaxy. So, the typical metal poor globular cluster has a metallicity about minus 2.5. So, any star which is metal poor than minus 2.5 is called extreme metal poor star. The theoretical prediction shows, the simulation shows that these extreme metal poor stars are polluted only by the POP3 stars. So, POP3 stars are the stars started with a Big Bang composition, and these extreme metal poor stars are polluted or got chemical imprints due to the POP3 stars explosive and nucleosynthesis products. And they don't have contribution from AGB stars because AGB stars pollute the ISM much later. And extreme metal poor stars also don't have contributions from any of the type 1a supernovae. And these stars are formed when the redshifts were greater than 4. And why do we care about studying these extreme metal poor star or EMP stars? So, they serve as a time machine to probe the early history of the galaxy. So, probing these early epochs at high redshift directly, we have to wait until the next decade of ground and space-based observatories. So, and due to the close proximity of these stars, we can study these EMP stars at much more greater detail at high resolution spectroscopy, and several key chemical elements can be studied, and that would be important to provide accurate information about the chemical history of them. The chemical history of metal poor stars are slightly more simpler compared to the stars which are in the solar neighborhood at solar metallicities, because these EMP stars would have received contributions only from few supernovae. So, that is why EMP stars are very important. They probe the epochs which cannot be directly probed now. So, these are some definitions. So, when we say metallicity, what it is, the square bracket Fe by H, it means the logarithm of number density of iron over hydrogen in the star minus the logarithm of number density of iron over hydrogen in sun. So, these are typical values, like Fe by H 0 means it is solar metallicities. So, that is similar to solar abundances, sun, and stars which are in the halo of our Milky Way, they have minus 1.5 as the typical median metallicities. So, that is much more metal poor than our sun, and objects which are the metal poor globular clusters in the galaxy are about metallicity of minus 2.5, and stars which are less than minus 2.5 in metallicities are called the EMP or extremely metal poor stars, and stars which are metal poor than minus 5, they are called hypermetal poor stars, and stars which are minus 7 metallicities and lower are called mega metal poor stars. And the POP3 stars are also the first stars. So, they are the ones which are formed with the Big Bang composition. And POP2 stars are the second generation stars. And POP1 stars are the solar metallicity stars. So, okay, here is a metallicity or the lower metallicity in perspective. So, different systems which are shown here, and their metallicity ranges are plotted here. So, what you can see is this is the Large Magellan Clouds and extragalactic globular clusters and Milky Way halo stars and damp Lyman alpha clouds, and you can also see metal rich globular clusters, the bulge globular clusters of Milky Way, and external globular clusters, external galactic globular clusters. So, what is striking here is the metal deficient halo stars. Currently, the most pristine old objects that can be studied are the halo Milky Way stars. So, that is why it is very important to get the information of the early galaxies. Halo stars play an important role. And there are a lot of searches for metal poor stars. The early searches focused on stars in the halo of the Milky Way, and these were primarily photometric searches. They use U minus B versus B minus V color. So, because these stars are metal poor, they have very fewer absorption lines due to metals. So, they are brighter and bluer compared to B minus V colors. So, for a given B minus V, the metal poor stars will have more bluer U minus B color. So, however, the broadband colors are not very sensitive to metallicities below -2, and the first pioneering survey was the HK survey by Beers et al. So, this uses a low resolution spectroscopy around the calcium K line, which is the very strong broad metallic line which is seen in the optical wavelengths for G2 K-type stars. And the later surveys were Hamburg ESO survey by Christleb, which uses the objective prism to identify metal poor stars. So, other large surveys which this decade is really good for this stellar archaeology. There are a lot of dedicated spectroscopic surveys like SDSS, Segway, RAVE, GALA and LAMOST. So, these spectroscopy surveys also have been really useful for stellar archaeology. So far, based on all these surveys, there are no zero metallicity stars found. So, does it imply that there is a critical metallicity that is needed to form small stars, that is low mass stars, or the accretion of metals from the ISM has significantly raised the metallicities? Modeling work by Friebel et al. Shows that anything greater than -7 metallicity cannot be due to accretion of ISM heavy elements. So, the currently known most metal poor stars are -5, 5.3, -5.5. There are 2 metal poor stars which are known, but interestingly both are carbon and nitrogen oxygen rich. So, if we look at only the iron abundances, they are -5 or so. However, their carbon abundances are about -2. So, this is really interesting why they have to be carbon rich. They are much different from the solar metallicity or solar neighborhood stars. The current record holder of the lowest metallicity, what we know, is -7.3. This comes from the survey in Australia, the SkyMapper survey, and however, this is also again very rich in carbon and nitrogen and oxygen. So, this star, though it has very low iron content, this can't be a POP3 star because it's still rich in other elements, lighter elements like carbon, nitrogen and oxygen. And we still don't know the origin of these enhanced carbon and nitrogen at very low metallicities. This is still a open problem in the stellar archaeology and metal poor stars abundance studies. So this is an example of spectra from HK survey. You can see the calcium K region, and the zoom in here, it looks like a very tiny calcium K, and you can see them further as you go into higher and higher resolution. Some of this calcium H and K component is due to interstellar medium. So high resolution spectroscopy is really important to further probe and catch very metal poor star. And this is again some stellar spectra to show a comparison of sun and other metal poor stars. So you can see the broad wings of magnesium and also iron lines in the sun, but the same lines are much weaker in the case of very metal poor stars. And here is the schematic chart showing the demography of EMP stars. So EMP stars in general are defined as stars which have metallicities below -2.5, and among them, interestingly, 20% of them are enhanced in carbon. And among these enhanced carbon stars, 80% of them are rich in neutron capture elements. So that clearly indicates that these could be due to AGB pollution. So these EMP stars, which are enhanced in carbon as well as the neutron capture elements, have had a binary companion which have gone through an AGB phase and also a mass transfer, and currently in a white dwarf evolutionary phase. So radial velocity follow-up of these stars have clearly indicated that most of them can be explained due to binary mass transfer. However, there are also a significant number of carbon enhanced metal poor stars which are more metal poor than the neutron rich carbon enhanced metal poor stars, and predominantly these are found at much lower metallicities, like the current record holder objects which are at -5, -6 and -7 and so on. So this needs further detailed study to look into the origin of these stars. And on the carbon normal branch, there are different types. We have alpha enhanced stars. So these are very similar to solar scaled stars, which have predominantly have contributions from supernovae which have polluted our halo stars. There are also alpha poor stars which would have likely come from accretion of satellite galaxies. And you would see in the later part of the talk that stars in the low mass galaxies like dwarf galaxies are alpha poor due to the low star formation rates. And there are also interesting R process enhanced stars. There are about a significant fraction, maybe about 1% of them are enhanced in R process. Actually, we have not found any stars at a significantly at the detection limit 0 R process rich star. So that is something which needs further study. So the R process enhanced stars among them, they have R process enhancement up to 100 times the solar ratios, and these are also subdivided into R1, R2 and R intermediate. So R2 stars are particularly interesting because they have uranium and thorium detection. So we can clearly detect uranium and thorium nuclei in these transitions in these R2 stars. So they show the smoking gun event of a supernovae explosion or a site that produced R process. Okay, since CEMP stars are the carbon enhanced metal poor stars are the most dominant fraction. So they have about 10 to 1000 times solar carbon to iron ratio, and the fraction also increase with lower metallicities. They have at minus 2.5, they have about 20% of EMP stars are carbon rich. At minus 4, about 40% of them are carbon rich, and below minus 5, we don't know any star which is not rich in carbon. The reason for such a large enhancement in carbon at low metallicity is one of the outstanding questions in the stellar archaeology. So, the possible suggestions are carbon cooling was probably important that enabled formation of low mass stars. So, the initial cloud itself is carbon enhanced to facilitate cooling and formation of low mass stars. And other possible sites like the early supernovae were faint, not energetic. The mixing and fallback has produced a large amount of carbon, or the IMF was very different for the first low mass stars. So, there were more number of AGB stars, so which has produced a large amount of carbon. Or we also do not understand any other possible selection bias in the studied sample. This is a example spectra from the Sloan Digital Sky Survey showing a carbon enhanced star. So, what you can see on the top plot, it assumes a solar ratio for carbon. So, this G band or the CH molecular band is not fitting quite well. So, the observed spectra which is shown in the black line is much more enhanced than the red synthetic model. So, you can see this is quite enhanced about at least more than 10 times the solar value. So, this carbon enhanced stars, CMP stars come in different flavors. So, we have already explained in some detail. So, there are carbon stars which have no neutron capture enhancement, and stars which have rich in R process, and CMP stars which are rich in S process, and there are CMP stars which are rich in both R and S process. So, we find that out of 80% of CMP stars belong to the CMP R plus S, and the origin of R process in these stars is still a puzzle, because if we look at the relative fraction of CMP S only and CMP R plus S stars, they do not match the pre-pollution of supernovae due with R process. So, this is something which we still do not understand. There are possible processes which were proposed, like intermediate neutron capture process with a AGB mass which are closer to super AGB stars, and so this is something which it's still ongoing work in this field. And this study of these AGB stars which are companions to these CMP stars also help probe what is the unseen IMF of the AGB binary. So, currently we are only selectively probing stars which are 1 solar masses and below, and which are low mass, but stars, the CMP stars which have unseen companion AGBs, so they belong to a mass range of 3 to 8 solar masses. So, this unseen mass can be probed by studying the CMP stars. So, this is again an example to show the really a strong lead line which is found in the CMP R plus S stars. So, lead is the third or the strong S process peak. It is one of the stable nuclei, and so they are produced in a large amount in metal poor AGB stars, and this can be seen in the spectra. So, this particular object is about 1000 times lead rich compared to iron for comparing the relative abundances of sun, these are 1,000 times lead rich compared to the iron abundances. Primarily due to large neutron to seed ratios at low metallicities. And so this is kind of solves some of the puzzles which were there in the solar system abundances, where lead was thought to be primarily coming from the radioactive decay of uranium and thorium. But with the study of CMP stars, now we understand a large amount of lead is produced by metal poor AGVs. So one of the possible solution which was proposed for CMP fraction and the connection to CMB, that is the cosmic microwave background temperature. So we still don't know the transition between a POP3 or heavy mass stars into the present day IMF, that is the initial mass function. The transition happened abruptly, or it was mediated by gradual change in the CMB temperatures. So this is the work by Tumlinson et al. Is in 2007. So at low redshifts, we have the gas cooling by metals and dust sets the lowest limit. So this is about 10 Kelvin. But at higher redshifts, the CMB itself, the background temperature itself, acts as a minimum ceiling temperature for the gas. So at different redshifts, at Z equal to 5, 10 and 20, the cosmic microwave background have temperatures 16, 30 and 57. So this sets the characteristic mass or the Jeans mass of this gas cloud, and this enables formation of bigger stars. So the transition from POP3 to low mass stars probably was mediated by the cosmic microwave background temperatures. And one of the prediction by these authors was the enhanced carbon rich stars, which will be found at different metallicities. So now we talk about this R process rich stars, which are again a significantly important fraction among the metal poor stars, and they are also very interesting. So these are R process rich stars, about 100 times solar R process value with respect to iron, and they are found among metal poor halo stars, and they are also found among few of the Milky Way faint satellite galaxies, like Reticulum is one of the galaxies which we see stars with large enhancement in R process. And these R process rich stars, some of them also show uranium and thorium detection. And these are the rare events where heavy elements production due to an explosive event can be captured. And these abundance ratios can clearly give clues to the physical conditions of these the site and the processes. And R process elements at different metallicities of among EMP stars also gives possible clues to the masses and various sites which can produce them. And this is, so any site which makes R process have to go through certain constraints, and one of these constraints are the universality of R process abundance ratio, which was observed in halo stars. The plot on the left shows the solid line shows the solar system solar R process pattern, and all the points show different halo stars which are enhanced in R process. So each of these halo stars would have got contribution by a single R process event, and this blue curve, which is the solar system or solar R process pattern, it is a cumulative effect of a large number of R process events. So a cumulative event, the abundance ratios which were produced by a cumulative event and also what is seen in individual R process event match precisely well. So this shows that any R process site which would be proposed should be robust and independent of astrophysical conditions, for example, mass of the star, and metallicities, and probably mass loss and other things. And this is again a plot to show the detection of uranium in one of these metal poor star and thorium detections. The neutron richness should be able to make robust R process all the way till uranium and thorium. That is again a stringent constraint on any sites that produce R process. And this uranium and thorium also acts like a independent, parameter independent cosmochronometry, and age can be estimated without assuming any models. And however, the age estimation based on these few detection, they show a large uncertainties. Primarily the detection of non-detection of lead abundances in these stars, and some of these R process rich stars also show higher uranium and thorium compared to europium. So, this is also something we do not understand. This is called actinide boost. So, once we understand all this, and with future facilities when we were able to observe lead abundances in this R process rich stars, they can act as a accurate chronometer for these metal poor stars. And this is another constraint which comes from observations. So, this clearly shows the two possible scenarios that can, or two possible sites that can produce R process. So, the current contenders on this is the supernovae and the neutron star mergers. So, they both have possible physical conditions that can make R process. So far, theoretically supernovae, making R process in supernovae explosions have been quite difficult. Only a narrow range of supernovae could make R process, but making R process all the way up to through thorium and uranium was found to be difficult for theoretical modelers. But the chemical evolutionary models, like the observations, for example, if you look at the iron versus europium abundances, the red dots show the observations and the black dots are the simulations. So, what is shown here are the neutron star mergers versus supernovae, and you can see that clearly neutron star mergers start to contribute to the R process production much later at much higher metallicities. So, they take the time scale of R process production is much later in the early galaxy. So, stars which are very metal poor and still have R process abundances or R process enhancement cannot be explained based on neutron star merger events. So, we need to understand this also gives possible constraint on the this evolution of merger scenarios. And this is a kind of a recap on the primary nucleosynthesis sites and timescales we had already discussed. So, supernovae have a time scale of less than 10 power 8 years, and AGBs have time scales greater close to 10 power 9 years, and supernovae type 1a have time scales about 2 into 10 power 9 years. So, this is one of the classical examples of how alpha enhancement relative to iron probes the star formation history of any galaxies. So, this plot is just a schematic diagram. So, what is shown in the x-axis is the is iron abundances, and y-axis is the alpha abundances. It could be any of these oxygen, magnesium and silicon abundances. So, alpha abundances are produced by massive stars, and massive stars also produce iron. However, type 1a supernovae only produce iron. They don't produce any alpha elements. So this plateau, what you see, the horizontal line, indicates the pollution only due to type 2 supernovae. And this knee is the time at which the pollution due to type 1a starts in the galaxy. So this is a very clear indicator of star formation history of a galaxy. The IMF, the level of alpha enhancement, depends on the IMF of the galaxy, and the slope and the knee of this diagram shows the star formation history. So more massive stars, example starburst, could result in very highly enhanced alpha abundances, and it could have the curve is much more flatter. The flatness part depends on the star formation rate. More for a longer duration of metallicities, if it extends further, that means they have highly enhanced star formation rates. And this is the example for Milky Way stars, and you can see the plateau, like so you can see at the knee occurs at metallicities of -1, and interestingly at -1 is when the thin disk of the Milky Way start to form. So the formation of disk and the type 1a contribution to the galaxy is kind of it's a coincidence that these two time scale matches for Milky Way. And if the lower plot shows barium abundances. Barium is a element which is purely made out of slow neutron capture, and their main contribution comes from AGBs. And you can see in the early epochs, AGB did not produce any S process, and the AGB contribution starts at a metallicities of -2. The earlier this barium abundances which are declining below -2, these contribution comes from primarily from massive stars, possibly weak R process. Okay, so these kind of plots is what is called chemically tagging, and this chemical tagging of individual stars can say a lot about the galaxy populations and the star formation history. And this is again this red points, what we shown here is for the Large Magellanic Cloud, and interestingly they have very similar alpha abundances, for example magnesium, but however they have very low calcium abundances with respect to the Milky Way halo stars. So this is something which we still do not understand, how there are two sites or different sites which make magnesium and calcium. And we can also see that the late R process and S process contribution for LMC. So they start to contribute at much higher metallicities. And these are for other dwarf galaxies, and clearly these follow this mass metallicity relationship of galaxies, and we can see significant offset between magnesium and calcium. This is something which is different for different galaxies. And for low mass satellite galaxies, we see the R process and S process contribution comes much later. That indicates the recent star formation. And this is again for another dwarf spheroidal. It's a sculpted dwarf spheroidal galaxies. This is again, it's a little more massive than other dwarf galaxies. So they are consistent with the lowest, the mass metallicity relations, following the mass metallicity relation of the galaxies, and the knee occurs at -1.8, and they don't have a late R process and S process contribution. They are almost very similar to the Milky Way halo stars. And the formation of these extremely metal poor stars in the Milky Way and satellites. So this is theoretical simulations. What you can see is the star formation begins. This is the top left shows the different redshifts and the star formation happening at different redshifts. And you can see that top is the highest redshift and to the low redshift. So you can see that the central regions of the galaxy start to form the first stars. And this is the ideal place for searching POP3 signatures. And for example, Milky Way, metal poor Milky Way bulge stars would be very interesting. And they are also equivalent to the high redshift H2 regions, because if we look at low density regions of Milky Way, the halo and satellite dwarf satellites, they do not represent the high redshift counterparts which we see, the IgM and the H2 regions which we observe at high redshift galaxies. They are not ideal counterparts. So Milky Way bulge, the metal poor Milky Way bulge can give a complementary information about high redshift studies. So searching for first stars among these metal poor Milky Way bulge stars are very challenging, and ISM pollution is also an issue. And satellite galaxies offer an easier avenue, but the caveat here is they are not the high redshift counterparts. And so in the near future, we won't be able to even observe such dwarf galaxies at very high redshift in the near future. So it's our best bet is to study these metal poor stars in the bulge. So this is again to summarize the chemical tagging of stars and probing the chemical history. So the key points here is the different masses of stars make different chemical elements, and these chemical elements are made and mixed into ISM at different time scales. Stars that are formed from these ISM carry the chemical imprints of this pollution, and hence these stars acts as a time machine to probe the early star formation history of galaxies. And here we have given the time scale, the stellar winds that produce carbon, nitrogen, oxygen and sodium from the massive stars. They are made at about 10 power 6 years, and type 2 supernovae make elements at time scale of 10 power 7 years, and type 1a supernovae, it's about 10 power 9 years, and AGB stars make their elements 10 power 8 years. So multi-element abundance ratio is a key to understand the star formation history and the mass assembly of Milky Way. And this is just to highlight one example of how difficult it is to study the faint dwarf satellites. So what is shown on the left is a halo field, and the dots, different colored dots are the possible candidates for a dwarf satellite galaxy. And so identifying them is really spectroscopically time consuming. Broadband colors are very difficult to remove the degeneracy between the age and metallicities. So spectroscopy is going to be very expensive, and these are so highly multiplexed. Future deep spectroscopy can improve such studies. And in summary, the EMP stars are have very different compositions compared to the solar metallicity counterparts. They are enhanced in carbon, nitrogen and oxygen abundances relative to iron, and it is quite common, and we don't understand this origin. The chemical signature of rare events can be found in these EMP stars, so they provide smoking gun evidence for these first stars. And stellar archaeology provides valuable information on the formation sites and star formation history of the galaxy.